dissolve, we won't refer salt as salt, we will call it dissolved cations and anions. So what is the source of those cations and anions in the seawater? And once in the ocean, what happened to those cations and anions? So to answer these questions, first we need to zoom out and take a look at the bigger picture. So today we will start with the plate tectonics, and I'm going to share my screen with you guys. Desktop, yes. Uh, okay, so what is plate tectonics? What does the theory of plate tectonics says? Plate tectonics, first thing, is the screen visible to you all? Someone needs to reply. Can you see the world map?
Yes, ma'am, it's visible.
Okay, thanks. So what does the plate tectonics theory say? It says that the Earth's surface is made up of plates. There are about 12 major plates. So these are plates. Okay, and this is a rigid part of the Earth, and that is called the lithosphere. All these plates, they're the rigid part of the Earth. They're called lithosphere. And these plates are moving relative to one another. Why are they moving? Because they're gliding over a mobile mantle, and that is called asthenosphere. So that's how the plates look like. Okay, this is lithosphere. This entire brown to black portion, that is lithosphere, and this lithosphere is actually gliding over the mantle. Do remember, this is not liquid, but it is so heat up that it is plastic, it is mobile, and this is known as asthenosphere. So uh, okay, the lithosphere is the outer rigid part of the earth, and asthenosphere is the mantle beneath the lithosphere. We have seen that already. So these plates are moving. So they can move either away from each other, or they can move towards each other, or they just can slide by each other. So there are three types of motions, and uh, technically speaking, there are three types of plate boundaries. The first one is this one, uh, transform fold boundaries. So these two are different plates, but they're just sliding past each other. There's the other one, when the plates are actually moving away from each other. And the third one is the convergent boundaries, where two plates are colliding. So one of them is actually going beneath the other one. This is known as subduction zone. We'll move back to the bigger picture. So why are we interested in what does seawater has to do with the plate boundaries, right? We will move to the convergent boundaries. No, first we will take the mid-Atlantic ridges. So these are two plates, and they are actually moving away from each other. This is North American plate, this is Eurasian plate, and they are moving away from each other. Where does it lie? We are talking about this picture. Okay, so this is North American plate and this is Eurasian plate, and they're moving away from each other. And here what we have got, see, do remember, the surface area of the earth is constant, right? So if the plates are moving away from each other, so they must be colliding somewhere. And when they're moving from away from each other, there is this new oceanic seafloor formation taking place. Okay, so mid-oceanic ridges, these are at the divergent plate boundaries. There is the formation of the crust taking place at the mid-oceanic ridges. See, this is actually the molten magma. Okay, and the temperature is really very high, and there are some fractures at the. Do remember where this is all taking place at the oceanic floor? Okay, not on the continental crust. This is all taking place at the oceanic floor. So this is a molten magma, and there are fractures along this boundary. There are fractures. So what happens? Water actually percolates inside those fractures. We can see in the next picture. So these are the fractures. Water percolates inside these fractures. And because magma is really very heat up, as soon as water comes in contact with magma, the temperature rises, right? And it becomes the when the temperature rises, what happens to the density of the water? Does it become lighter or heavier?
It becomes lighter.
It becomes lighter. So buoyancy, right? So dense, it's very light. So what will happen? It will rise up again because it's very light. And when it it rises up with a lot of force, with a lot of pressure, and we got such formations at the oceanic seafloor. Okay, this is the water rising up after coming in contact with the mantle. It doesn't actually come up within in the contact of the mantle. It just goes beneath, and the temperature rises up so much that it becomes so buoyant and it rises up with the force. And we get, and these are called black smokers. Let's look into the mechanism when water is going inside, percolating inside the oceanic crust. So it has become very acidic. It's really warm and it's very acidic. And this is all basalt. This is the oceanic floor. So it reacts with the basalt. It reacts with the mineral present in the sea floor. Okay, and then it rises up. And once it's back to the ocean, those dissolved cations and anions, those dissolved minerals are going to be back in the seawater.
Ma'am, I have a doubt.
Yeah.
Is there any specific reason that the plate boundaries are only formed in the oceanic regions, not in the continents?
Okay, not into the continents. Good
Ma'am,
question.
I too
Haha.
have a doubt.
Yeah.
Yeah. So, why these plates are broke actually? Why there is a fracture in between them?
Okay. First of all, let's try to understand that why there is a fracture in between them. Okay. We have molten magma, and how did the crust form in the first place? Have you guys done any course on basic geology, or is this your first course in earth science?
Yes,
Yes,
this is
ma'am.
the first course.
This is the first course. Okay. So plate tectonics will be discussed in way more details in the second course, I think origin and evolution of the earth. But the idea of discussing plate tectonics is here is from the seawater perspective. Why seawater is salty? Why do we have cations and anions in seawater? Okay, and as for why there are fractures, first of all, we will discuss they are moving. The plates are actually on a mobile surface on the mantle, which is very plastic, so they can move, they can glide. Okay, so once plates start moving, what happens? There's not much space, so they are going to collide with each other. And when they collide with each other, at some other place, there should be new plate taking over because the surface area of the earth is constant. And as for the question, why continents, why there is no, uh, what do you say? Why there is no new plate formation taking place in the continents. Actually, do I have the rift? Uh, I will move to the other slide then.
Ma'am,
Yeah.
suppose there were
Huh.
no tectonics or means there were no
Yes.
breaks in
Yes.
on the surface. What would happen means suppose consider a scenario like there is
Like
there
like
there
Mars. Mars doesn't have any more plate tectonics.
yeah. So
So,
what
so we would be a dead planet like Mars.
means what means means can you justify how it will be dead planet? I couldn't understand that. Uh,
Okay, guys, we are diverting from the topic, but that's completely all right. Oh, in bigger picture, what is what is the plate tectonics doing? They are recycling the material through the earth, the atmospheric CO2, the minerals. Okay, and if we don't have plate tectonics, okay, I'm going to share my screen again. We will go one by one. Okay. So someone asked why there cannot be what new plate formation at the continental crust. Actually, it starts this way. These are the continental crust, right? And here we have the mantle plume. And mantle plume, because it's heat up, so continental crust starts breaking up. Okay, moving away from each other, and we get a rift valley in between. And over time, what happens? The water takes over here. Okay, these two plates keep rifting away. These two continental plates keep rifting away, and finally, this portion, it becomes so fragile and so thin that the mantle is actually able to come over the surface. Am I clear the why we don't have new plate formation on the continental crust? It starts with the continental crust. Okay.
Ma'am.
Huh?
Yeah, recently there was in Africa there were recently there was a huge gap in between.
Yeah, you are talking about this one. This
Yeah,
one.
yeah.
This is not
Uh,
recently. You don't say it recently. It's
no, 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 no,
million of
no,
years of phenomenon.
no, no. I think this is not the recent one, but
Huh.
I have seen it. So
Yeah. Okay.
they have found a very big gap in between surface.
Yeah. So what is happening? This is again two. This is the continental crust. Okay. And the rift valley is taking over here. Can you see it? There is this rift formation here, the same African plate.
Yeah,
Okay,
yeah, yeah.
eventually, what will happen? This continental crust will move away, this will move away, and the oceans will take over. When the continental crust move away, whatever we left with is actually the very thin crust. Okay,
Acha.
and finally, it's so thin that the mantle can percolate over it. Mantle can rise from these plates, from these fractures, and then it becomes mid-oceanic ridge like this one. And similar, the same thing is actually happening here. Finally, eventually there will be a ridge valley. Okay, and the crust will be so thin that the mantle will start forming new plate, and that would be oceanic plate. Clear? So Africa will eventually be divided. Who asked me about the continental plate?
Me.
Okay, so does it make sense? Like, are you able to understand?
Yeah.
Right. So it
Yeah.
actually it's not like, I
New
mean,
formation of a
eventually, yeah,
continent.
eventually it leads to mid-oceanic ridges.
Acha.
Okay. And what was the
Okay.
other question about?
Why there is a fracture in between continental?
Okay, that is because of mantle convection. Okay, we got those spikes in the mantle. So beneath continental crust, it's all mantle, right? So once in a while we get those spikes. The temperature gets so high, and when the temperature gets high, what happens? The density decreases, right? Buoyancy. So the mantle is actually getting lighter, and it's there's this upward plume. Okay, the manifestation of this upward plume on the surface is this ridge, the Rift Valley. So that is the mantle convection, and I don't think we should dive down into that. Right here. Okay, this is mantle convection, and here we get this plume, and we get the ridge here. So we get those spikes of the mantle that are actually less denser, and that's why we get this plume formation. And as the manifestation of this plume, we have ridges. Clear?
Ma'am,
Huh.
ma'am,
Yeah.
does spin of the Earth or revolution of Earth around Sun affect the formation of plate tectonics, or is it just just that dense mean? Does it does it mean how- affect where the plate tectonics will be formed, or what kind of plate tectonics will be formed at which place on the surface of it?
Uh, as far as I know, it has to do with mental. Okay, interior of the earth and revolution of the earth. I really never thought about it, and I have never read about the effect of revolution of earth on plate tectonics, right? That's what you are asking.
or
The revolution and the
uh,
position of the earth.
spin you can consider me it also spins like
Okay,
about,
rotation of the earth.
yeah, rotation about yeah, and also
Rotation
the
of the earth.
triangle, that precession angle, does it affect
The tilt,
where,
you mean to say?
yeah, where plate tectonics will be formed or
Uh, uh, I I really don't know. I don't get any correlation between the rotation of the Earth and plate tectonics. They might be, but I really don't know. I have never read about this. But like, did you come through some article? Hello, hello. Have I lost my connection? Hello.
Yeah,
hello,
ma'am.
you said something I couldn't hear.
Okay, I said, like, I really don't know. I have never read about the connection between the plate tectonics and the rotation of the earth, the spin and the tilt. Never heard of it, because this is the interior of the earth that's driving the mental convection. And where is the source of energy in the interior of Earth? That's actually the radioactive decay of uranium and thorium. That's the source of the heat in the mantle. And on the surface of the Earth, the source of the heat is actually sun. So the tilt, uh, I really don't know, is there any connection? Okay.
Okay, ma'am.
So can we move forward?
Yeah, ma'am.
Okay, we had discussed plate here. We have discussed types of boundaries. And okay, the plates converge to and they collide with each other. So the ocean, am I audible because it says bad network quality?
You
Yeah,
are
ma'am. You're
audible.
audible.
Okay. So the conversion can be either continent convergence, and the weathering of those mountains are going to be the ultimate source of cations and anions in the seawater. Okay, we will discuss that in details, or we can have oceanic crust subducting beneath another oceanic crust, that is like Mariana Trench, and we can have ocean and continent subduction. Anyways, the important one here is continent, when two continent plates collide and we get the mountain formation, and Himalayas are the result of those mountain formation. And hydrothermal circulation, the water percolating through the fractures in the sea floor and finally rising up because of buoyancy. And when it's heat up, it's very acidic and it dissolves the mineral in at the oceanic floor. And that dissolved water comes at the surface. At the surface means at the sea floor surface, and then it mixes back with the seawater. And hence, hydrothermal circulation is actually source of cations and anions in the seawater. It's also the sink, but for magnesium and sulfate. But otherwise, for other major cations, hydrothermal circulation is actually the source. Okay. Let's
Ma'am,
move
I have a
to
doubt.
where.
Uh,
Yeah.
Ma'am,
Hmm.
yeah, so I have the doubt regarding why magnesium and sulfur are deposited at bottom of the sea floor.
They are not exactly deposited. So what happens here? So when the water percolates through here, you see magnesium from the seawater. Magnesium is actually reacting with the minerals present here, with the basalt here. Magnesium is actually replacing the calcium, and calcium from that mineral is actually sent back to the seawater. Okay,
Okay.
so all uh, like in bigger picture, what's happening? We have minerals at the sea floor. When this hot acidic water percolates through the sea floor, magnesium is stripped from the seawater. Magnesium actually replaces other cations that were present in that mineral, and those cations are released back and they reach the surface. And now I don't have a very specific answer why magnesium and why not another cation, but magnesium. Okay, magnesium is taken from the seawater, from this hot acidic seawater, and calcium and sodium and potassium actually get dissolved in the seawater and reach back the ocean.
Okay, ma'am. Thank you.
Okay. Remember the slide where Sir had said that what are the inputs to the seawater? Someone remember from the previous lecture what are the what are the inputs to the seawater? One of it we just discussed, right? Okay, reverse dust and gas exchange and hydrothermal circulation as well. So now we will move to reverse part. Do I have it actually? Okay, in general, what is weathering? So weathering is actually dissolving the rock material. We are talking about chemical weathering here. Okay, so that is aided by small amount of acid in the water. That could be carbonic acid or sulfuric acid. So where is uh, can anyone tell me just what is the difference between rock and mineral?
Rocks are composed of many minerals or one mineral.
Yeah, right. So minerals are just the chemical compounds, and rock is yeah, rocks are composed of many minerals. Okay. Yes. So we will look at the chemical weathering. So for chemical weathering, we need a mild acid. So where does this acid come from? This is a CO2 from the atmosphere. This is H2O, water, and this is anorthite. Anorthite looks something like this. Okay, so when the and H2O plus CO2 is going to combine and form carbonic acid. So when this carbonic acid reacts with anorthite, what are the products that we get? First one is clay, kaolinite. ठीक है? The first one is clay, and another one is calcium bicarbonate. So this calcium had come from this part. Now this calcium bicarbonate further breaks down into calcium 2 positive, the cation, and the bicarbonate. Okay, out of these two products of the weathering, which one is going to stay back and which one is going to be mobile? See, the clay is going to stay back, and the cation part, these parts, they these are the actually dissolved parts, right? So they will move with water. Move with water. What do I mean by that? Eventually, they will find their way in the rivers and they will reach the ocean. Let's talk about the orthoclase. Orthoclase is actually potassium feldspar, and it looks something like this. So, what is going to be the end product of weathering of the potassium feldspar? Of course, the potassium cation, right? And the other part of the weathering of this mineral is going to be someone
Okay.
the clay, right? So orthoclase is going to give us with potassium and the clay and silicic acid, which is going to be silicate, right? Rivers also bring the silicate to the ocean. Albeit this is sodium feldspar, and this is going to provide the sodium cation. Therefore, the rivers are going to bring many cations to the ocean. Now look at this one. So what this is actually weathering, right? CO2 plus H2O is going to rise to carbonic acid, and that carbonic acid is going to react with the rocks. And finally, we will get the cation part, which is mobile part, and the rivers are going to bring this cation to the ocean. Eventually, what will happen? We should have a buildup of cations in the ocean, right? What do you think about the salinity? Is the salinity of ocean changing? Is it building up over time? Yes, no?
Can you repeat it again, ma'am?
Uh, the salinity of the ocean, like the rivers are bringing the weathering products of the continental rock. Okay, what are those products? The mobile products. Those are cations. Calcium cation, magnesium, sodium, right? So rivers are bringing those cations to the ocean, and those cations and anions are the reason for the salinity of the seawater. So is the salinity rising over time? Because rivers keep on bringing the cations, right? Cations and anions. So the salinity of the ocean, is it rising over time? Is it building up over time?
Maybe might be some equivalent
Uh,
between the amount that is brought up and the amount that gets precipitated.
Harish, I think, uh, could you please repeat again? You are not audible actually properly.
Hello.
Now please.
No, I am saying like there might be some equilibrium that exists. So possibly maybe some sodium ions might be coming in, but some sodium ions might get means salts might get precipitated at the ocean bed. Uh, so it would be constant over time, won't build up over time.
Right. So, I wouldn't say this. So salts are precipitating. We'll discuss why they are not
Ma'am,
precipitating, oversaturated and undersaturated. Uh, okay. And the other thing is, these are the sources. So at the other end, we have sinks as well. The sink and the sources are at equilibrium with each other, and that's why we don't have the salinity buildup.
ma'am, I
Yeah.
also think that what due to evaporation, salinity remains constant.
Due to evaporation, what is actually happening at evaporation?
Actually, water gets evaporated, right?
Yes,
So,
so the salts will
uh,
be left behind.
I don't know.
Yes, they will be. It's just the
Acha.
evaporation of the water. Okay, just H2O.
Acha.
Okay. We don't
Okay.
have. Do you think the rain is actually salty?
It's
Salty like
acidic.
seawater?
It depends on
Huh?
it depends on the I mean it depends on the place where we live.
It
You know,
depends on. Okay.
if you are if you are in some pollution in some populated area, then it might be some acidic rain, that kind of stuff.
Yeah, so acidic rain and salty rain are different. Okay. So
Yeah.
those acidic rain is actually this H2 reacting with CO2 or with the pollutants of the atmosphere.
Yeah.
Okay, that's how we get the acidic rain, and that acidic rain actually leads to weathering of the roads. Remember Taj Mahal getting yellow in
Yeah.
color?
Hello.
So that is actually weathering.
Yeah.
Okay, but that is not salty. It doesn't have the cations and anions. It doesn't have NaCl in it. It doesn't have potassium sulfate in this.
Okay.
Okay,
Okay.
so the rain is not acidic. Sorry, it's not salty. It
Something.
it might be acidic, as you said, depending on the area, depending on the region, depending on the atmospheric condition. But rain is pure water. Okay,
Yeah.
so where were we? We were looking at why we don't have salinity buildup. And I think sir will discuss that in detail with the two box model. Okay, and now we will move on. So right now you all understand what is chemical weathering, how is it taking place, and what are the end products of weathering. Okay, any doubts on chemical weathering?
No, man.
No, right? Uh, Now let's move to the sink. Uh, this is primary production. Uh, Photosynthesis, CO2 plus H2O plus energy give rise to glucose plus oxygen. Uh, in more detail, let's talk about the photosynthesis in the marine environment. Okay, this is the complete equation of photosynthesis. So what are the reactants here? What are CO2, nitrate, phosphate, water, and energy. And this is the final product of photosynthesis, the organic part, and this is oxygen. So in our this is inorganic part. This is inorganic. CO2 is inorganic. The end product of photosynthesis is actually the conversion of those inorganic minerals or inorganic nutrients into organic matter. Okay, so let's draw the profile of nitrate. What do you think in seawater photosynthesis take place till what depth? Huh?
Maybe 150 meters something.
Yeah, exactly. Something like 100, 150 meters. Okay, so on y-axis we have depth. And on x-axis we have the concentration. From the previous equation, what do we see? What are the key requirements for photosynthesis? CO2. And what is the source of CO2? For the marine photosynthetic organism, the life form, for the marine life form. Primary producer, what is the source of CO2? Hmm?
Carbon.
Uh, I mean, CO2 will be coming from atmosphere, right? CO2 will come from
Ma'am,
the
I have a question.
atmosphere, finally dissolve in water and form bicarbonate ion. In carbonate ion, we will move towards that. Huh. Someone has a doubt?
Hello.
Uh-huh.
Yes, I have a question
Yeah.
that CO2 is pretty soluble in water. So,
Yeah.
why are the major source of CO2 is the atmospheric CO2. I mean, organisms are also excreting CO2 with their breath.
Right. Organisms are not taking directly from atmosphere. So CO2 from the atmosphere is going to dissolve in seawater and then dissociate into carbonate and bicarbonate ion. So those bicarbonate ions are going to be incorporated by marine primary producers. Okay.
Okay, but I asked about the source of the CO2. I mean, atmospheric is I mean, a big source, but also the respired out CO2 is also important, right? I mean,
The
there are many organisms
respired
in ocean.
the respired CO2 in the ocean. Yes, we will look into that. Okay, we will look into that. The
Okay.
respired part of the CO2. Okay, for photosynthesis, you need CO2 that you get from the atmosphere. It dissolves in water and dissociates. You get a bicarbonate ion. From the where do you get the nitrate in seawater? It's actually in seawater. Okay, and the phosphate is also in the seawater. Now we are going to look at the nitrate profile with depth. Right. So what happens at the surface? There are primary producers, right? So those primary producers are going to incorporate nitrate. So what will happen to the concentration of nitrate at the surface?
It will decrease.
It will decrease, right? Uh, let's say these are first 150 meters or 100 meters, something like that. This is 150 meters, right? So it will be very less on at the surface, and eventually what will happen? Uh, the primary producers, they are consumed by the consumers, right? That's how the food chain survives. At the end of the food chain, we have primary producers, and then we have consumers, right? First level of consumers and secondary consumers. So in the water, what will happen? The layers beneath will be habituated by consumers. The first layer we will have photosynthesis and of course consumer, but beyond 150 meter we will have only consumers. What is the reverse reaction of photosynthesis? The reverse
Respiration.
phenomena? Yes, respiration. So this will be respired back, this organic matter will be oxidized and respired back, and those nutrients will be released back in the water. And of course, CO2 will be released back in the water. So what will happen with death? These nutrients are going to be released back. Simultaneously, let's look at what will happen to the oxygen. What do you think should happen to the oxygen?
It should be a mirror image of that graph.
It should be the mirror image of that graph, right? So at the surface, oxygen is being produced by primary organisms, by photosynthesis. So something like that. And at depth beyond what is actually happening, oxygen is consumed. By which process oxygen is consumed?
Respiration.
Yes, respiration. So the oxygen is consumed and hence we get the decrease in the level of oxygen as we go deeper in the water. Hence, nitrate will be increasing because respiration is releasing nitrate back to the seawater. Okay. Then, deep water doesn't have much of the life. Most of the life is actually on the top surface of the water, let's say up till about 500 meter, 500, 600 meter. Okay. So the role of biology is still the surface of the water. We have biology at the oceanic floor as well. Okay. But in between, we don't have much of the biology. So effect of the biology is seen till here. And hence the nitrate maxima should be where we have oxygen minima or oxygen maxima. What is this depth known as?
OMG.
OMZ, right? Oxygen minima zone. So that should be the nitrate maxima. And hence the profile something like this. Did you guys notice that oxygen? Haha.
Ma'am, there you made like oxygen started increasing after OMZ level. I
Yes.
didn't quite understand.
Okay. So that will come with dissolution of gases in water. Okay, the deep water, what is the temperature of deep water? It's quite low. It's very cold, right? 2 degrees Celsius, 0 degrees Celsius, something like that. Right? Moreover, this is high pressure, very high pressure. So the deep water gas will have
Yeah,
relatively
more oxygen.
more oxygen.
More
Right. So that's why
Henry's
it
law. Yeah.
starts increasing. Okay, so we are clear about the nutrient profile. So phosphate will also have similar profile, right? Because phosphate is also one of the nutrient.
Ma'am,
At, huh?
uh, in NO3 minus curve means
Yeah,
concentration curve,
right, right.
it should also increase with depth, no? Because means
Because
somewhat after that OMZ level, it should also increase some to
like
some
this.
extent. Yeah,
Why so?
means depth is increasing, so pressure is
Nitrate is
increasing.
not a gas. It's a dissolved. It's a
Okay.
dissolved nutrient in seawater. Okay.
Okay. Okay. Yeah. Yeah. Okay.
Okay. Oxygen
Okay.
is only the gas present here.
Hmm.
So
If
yeah.
so, if it was NO2's gas, then what would be profile like? Uh,
Okay, if it was nitrogen gas, then nitrogen is very inreactive gas, right?
yes.
Mm-hmm.
Yes, ma'am.
So what should be the profile look like with nitrogen? Something like this. Okay. Um, Something like this. So with pressure and with temperature, you get more of nitrogen, but otherwise the biology doesn't have any role to play in the depth profile of nitrogen. And it's actually more or less straight profile. Okay, when you look here in the concentration, so the increase in the concentration percentage wise would be very less. This is very exaggerated plot. Okay, but yes, the temperature and pressure have the effect on the solubility of the gases. So are we clear on how would a profile of nutrient look like, or oxygen, right? We can move on. Okay. We have discussed this. We have uh, so biology is actually the sink for the nutrients, right? And respiration is releasing back those nutrients. Now let's talk about the solubility of the gases. Another input to seawater is through the atmosphere. And what is atmosphere going to provide? Only gases. So A just A stands for any gas in the atmosphere. A gas in is in equilibrium with A aqueous. So how do we derive Henry's law constant? Let's look into that. At equilibrium, we all know about this equation, right? Equilibrium constant. This is valid for salt solution as well. This is valid for acid and base reaction as well, and this is valid for solubility of gases in liquid. Now we want to substitute this A gas, the concentration of gas, to the pressure of the gas. How do we do that? Do we have the relationship between the volume concentration of the gas and the pressure? Yes, we do have, and that is ideal gas law. PV is equal to nRT. N by V is actually the concentration of the gas, and that can be equated to pressure by RT. Now, this RT is more or less constant, right? So, what do we get? A aqueous is equal to KRT, K from equilibrium constant, divided by RT. RT is coming from ideal gas law into pressure of that gas. So we get a new constant, and that is Henry's law constant. So A aqueous is equal to Henry's law constant into pressure of that gas at the surface of the ocean. So A aqueous, we can this is valid for oxygen, this is valid for all the gases in the atmosphere. What do you think will happen with temperature for the solubility of the gas? Increase or decrease?
It will decrease.
Yes, why would it decrease?
Because the RMS velocity is going to increase. So the molecules will escape to the surrounding.
Kinetic, right? Temperature determines the kinetic energy of a gas, and hence, as the temperature increases, the velocity of the gas particle increases, right? So, colder the liquid, more the gas soluble in that liquid. Okay, and we can see that relationship with temperature. Now, there are two things that are very noticeable here. As the temperature increases, the solubility of the gases is actually decreasing. Helium doesn't have much effect with temperature. And then another thing is this decrease is not linear with temperature. And not every gas has the same solubility. And there's a relationship in the gas solubility and the molecular size of the gas. So as the molecular weight goes up, what do we have? It is more soluble in the liquid. Okay, and as the temperature gets warmer, the gases escape out of the liquid. And about the salinity of the solubility of the gas, is salinity going to affect the solubility of the gas? That was in the previous lecture. Yes, no? If we have fresh water and if we have sea water, what do you think in which water the gases are going to be more soluble if they are at the same temperature?
They'll be
Mm,
less soluble in the water that contains more solute because they will get less room.
yes, that already has more ions present. The system that already has more ions present will have the less solubility, will accommodate less of the gas. Okay, with that, we have covered more or less, at least we have covered. Okay, now we are clear what are the sources to the seawater. The rivers that are bringing the cations, the weathering products of the rock to the seawater. Another one is hydrothermal circulation. As the hot water percolates to the interior of the earth, it dissolves the mineral and bring back them to the seawater. And the other source to seawater is the atmosphere. Atmosphere gives oxygen and all the gases that are present in the oxygen. CO2 is also the source. CO2 is also coming from the atmosphere. Someone asked me, what about the CO2 that is respired back, right? Mm, now, CO2 is actually a very reactive system in liquid. Yes, this is the one. So, as soon as CO2 dissolves in H2O, in water, it forms carbonic acid. Now, this carbonic acid is not very stable. At the what is the pH of seawater? Is it less than 7 or more than 7? Or is it 7?
I guess it's a little alkaline.
Mm, okay, so yes, it's 8.1, but it is getting acidic as we are dissolving more and more CO2 in water. As the anthropogenic CO2 in atmosphere is increasing, it's getting acidic. By acidic, we don't mean it has crossed 7. We just mean that the pH value of seawater is decreasing. Okay, so as soon as CO2 dissolves in water, it forms carbonic acid, and carbonic acid dissociates into bicarbonate and carbonate ions. Okay, and this plot actually dictates how much carbonate ion we will have. Sorry, how much carbonate ion we will have, how much bicarbonate, and how much CO2 we will have. So let's say right now we are at something like 8.1. So the majority of ions is actually the bicarbonate. Do remember this is actually logarithmic scale, not the absolute concentration. Okay. So at 8 bicarbonate ions, dominates over carbonate ions and dissolved CO2. If we move towards more acidic system, something like this here, okay, so the concentration of CO2, or I should say the concentration of carbonic acid, will increase. Uh, Keeping this in mind, let's try to draw the profile of the total carbon total carbon in seawater with depth. Okay, so what is total carbon dissolved inorganic carbon DIC? That is concentration of carbonate ion plus bicarbonate ion plus CO2 aqueous. Okay, that is known as dissolved inorganic carbon, and that's what we are going to draw in here. Yes, so what will happen at the surface because of photosynthesis? We will have more CO2 or less CO2?
Let's say to.
Less CO2. And what will happen at OMC?
That
Because
will
of,
reach probably the maximum. I don't know.
yeah, exactly. So something like this would be the profile of, this is DIC. DIC is dissolved inorganic carbon. Do remember, we are not talking about the organic carbon. We are not talking about, uh, which slide was that? Yes, we are not talking about this part. Okay, this has been incorporated into an organism. It's no more available to the seawater. It's no more dissolved to the seawater. So when we get OMC, that's where DIC is going to reach the maxima. So at depth again. All right. So DIC has what? A very similar profile as that of a nutrient. And what else can we discuss? Have you guys gone through the assignment? Are we clear on what we have discussed in today's lecture class?
Yes, ma'am.
Okay.
Now I
Have
have
you?
a question regarding the
Yeah.
assignment question.
Yeah. Sure.
So there, capital T represents in one question temperature in
That is
Celsius.
temperature. Yeah. Okay. Go ahead.
It was in Celsius, I suppose. And
It is in
in the later
Celsius.
part, yeah. So in the later part of the question, there were a formula regarding some expression for rho naught and A, B, C parameters. So there
Yes.
also it was given small t. Is a small t in
Yeah.
Celsius, right?
That is Celsius, right?
Okay, ma'am. Thank you.
Okay. Any other doubts from the assignment? Now, this capital T, as it says, this is a function of temperature degree Celsius. This is degree Celsius. And how are you guys going to solve this equation? Hmm? Either use Excel or MATLAB. Okay. The idea here is not for you guys to remember this equation, just to get the feel of it. How does the density change with salinity and temperature? Okay. Any other doubts from this assignment? Uh, if you don't have any doubts from sir's previous lecture or from today's class or from assignment, then we can end the session here.
Ma'am,
Yeah,
I lost connection in between. You were
yeah.
telling like what is the pH of means what's the means seawater is acidic or basic. So its pH is around 8.3. Then how it is
Yes.
acidic?
Yeah.
How it is acidic? I didn't get that part.
No,
Means
no,
it
no,
is
no.
acidic or
Seawater is pH. If pH is more than 7, then definitely is alkaline. But as the concentration of CO2, as the concentration of anthropogenic CO2 in atmosphere increases, that means more of the CO2 is dissolved in seawater. And as soon as CO2 is dissolved in seawater, it dissociates, it forms carbonic acid, and carbonic acid further dissociates into bicarbonate and carbonate ion. And this gives H plus. So as the concentration of H plus increases, what happens? The solution becomes acidic or more alkaline.
uh, it will become acidic.
Yeah. So the seawater is gradually becoming acidic. But what I meant is, it doesn't mean it has crossed the value of 7. It has not become less than 7. When people say seawater is becoming acidic, they don't mean that the pH has become less than 7. It just means that the pH is decreasing. It is moving towards acid. Okay, that's what I meant.
Okay, ma'am. Got it.
Okay, yeah. And any more questions? If not, then